Today we will discuss first year chapter number 8, gravitation. So this gravitation topic is almost similar to second year electrostatics, except 2 points: one, orbital velocity; second, escape velocity. First we will discuss Newton's law of gravitation. Newton's law of gravitation. Newton's law of gravitation. This Newton's law of gravitation is similar to our electrostatics Coulomb's law. This Newton's law of gravitation deals with force between two point masses, whereas in electrostatics Coulomb's law deals with force between two charges. It was dealing with force between two charges. Newton's law of gravitation deals with force between two masses. The difference is, in electrostatic, the force may be attractive or repulsive, but in gravitation, force is always attractive in nature. Okay, let us see what it deals. First, as I told, it deals with force between two masses, that is a force between two point masses. Let M1 and M2 are 2 point masses separated by distance r. According to Newton's law of gravitation, here according to Newton's law, M1 attract M2, that is M2 experiences force this side, whereas M2 attracts M1, therefore it experiences force this side. According to this, force between M1 and M2 is directly proportional to product of their masses and inversely proportional to square of distance between them. If you combine these two, I can say F proportional to M1 M2 by R square. To remove this proportionality sign, we can add a constant called G. M1 M2 divided by R square, where G is called as proportionality constant and it is named as universal gravitational constant. Let's see about G. Here about G. As you know, it is first determined by Cavendish using torsional balance. Second, its value is G is equal to 6.67 into 10 to the power minus 11. Its SI unit is Newton meter square per kg square. So this is in SI system. In CGS system, I can write directly also, that is G is equal to 6.67 into 10 to the power minus 8 dyne centimeter square per gram square. It is in CGS system. Even if you don't know this value, you can arrive also. Example, see, G is equal to, in SI system, we are writing 6.67 into 10 to the power minus 11. It's a Newton. In SI, in CGS it is a dyne. You know, 1 Newton is equal to 10 to the power 5 dyne. 10 to the power 5 dyne. Meter. So we know 1 meter is equal to 100 centimeter. 100 is nothing but 10 to the power 2 centimeter. It is square. kg means kilogram. Kilo means 10 to the power plus 3. 10 to the power plus 3 gram raised to minus 2. If you simplify, 6.67 into 10 to the power minus 11 into 10 to the power plus 5. 10 to the power plus 2 whole square means plus 4 into 10 to the power plus 3 raised to minus 2 means it's minus 6. Remaining as it is dyne centimeter square per gram square. See here, minus 6 and it is plus 5 means minus 1. It's a plus 4 means plus 3. Plus 3 minus 11 is minus 8. Therefore 6.67 into 10 to the power minus 8. Right? So this is in CGS system. Second, after this value, next dimensional formula. That already we arrived in system of units and measurement. I don't want to go in detail once again. Third, this is universal constant. That therefore its value is independent of its value, G value. Value of G is independent of first, nature of material of two bodies. Second, it is independent of size of the two bodies. Third, it's independent of medium between the two masses. So this is our G. After this G, let us come to about the forces. That is about the force. Now about force. See, as you know, force is a vector physical quantity. Therefore, it can be added vector algebraically. Next, means it obeys vector sum. See, according to this, if we have one mass, so total force on this mass is equal to vector sum of forces due to other masses, that is F1 plus F2 plus F3 plus dash dash. Therefore, number of forces on this mass is equal to number of masses present around this particle. Next, as you know, suppose if we have two masses M1 and M2. Now M1 exert force, say F, when there is only m1. Suppose if there is once again m3, m4, m5 and so on. Here m3 will exert force here, force on m2 by m3. Here force on m2 by m4, force on m2 by m5, like this. When only m1 is there, force on m2 by m1. Only m1 is present and force is F21. Even when m3, m4, m5 comes, then also this F21 remains same. That is, force between the two masses is independent of presence of other masses. Okay, so next. After this, I think it is not necessary to write in vector form because already we have studied in electrostatics. Even though, let's try. See, here is easy way to write in vector form. Say it is m1, and it is m2. You know, to locate the position of m1 and m2, we need a coordinate system. Then let R1 is a position vector of m1 from origin. R2 is a position vector of m2. Then, okay, once again come to the basic. Force. Just now we have written this as F is equal to capital G m1 m2 divided by, this is the distance square. What is this distance? I'll take later. See, as I told you in previous classes, now this is in scalar form, no direction. To provide the direction without changing the magnitude, we have to multiply by a unit vector. This r cap is a unit vector. When you multiply by unit vector, then F gets a direction. Then direction of force is decided by direction of unit vector. Example, see, if I want to write force on m2 by m1. Force on m2 by m1 means m1 exert force this side. This is called force on m2 by m1. Then direction is towards m1. That I can write capital G m1 m2 by r square. Here r cap. The direction of r cap is from m2 to m1. You can write from m2 to m1. From m2 to m1. Okay. See, this can also be written in vector also. This is in unit vector. In vector form, as you know, unit vector can be written as vector divided by its magnitude. This also we have studied in electrostatics. So directly I can say capital G m1 m2 divided by r cube, its vector r. Okay, right. See here in vector also I can write. See capital G m1 m2 by, see here, how do you write this vector? Vector 21, its model magnitude is like this, cube. Sorry, here it is. Sorry, right, it's correct. Here is a cube. Then how do you write R21? This also we have studied in electrostatics as capital G m1 m2 by, see, always this vector can be written as final minus initial. The final is R2, vector R2 minus vector R1. Here it is modulus of R2 minus R1 Q. So this is in vector form. Okay, if you want to get a copy. So based on this, I can go for some examples. First, a simple example. Consider it is m1, it is m2, separated by distance r in vacuum. So now force between them is F. Now between same two masses m1 and m2, now a medium is placed. It may be other than vacuum and air, maybe water or something. Now the force is say F dash. Question is, what is the ratio of F and F dash? What is F by F dash is the question. It is my example number 1. Okay, see the solution. So as we know, force between two masses is given by capital G m1 m2 by r square. If you look at case 1 and case 2, in both cases m1 and m2 are same, and in both cases distance is also remains same. You know capital G, this value of capital G is independent of medium between the two masses. Hence for both cases capital G is also remains same. Therefore I can say force in case 1 and force in case 2 are equal. Therefore what will be the ratio? F by F dash. If they are equal, then ratio will be 1 by 1 or 1 is to 1. It's my example number 1. Now example number 2. Example number 2 here. So this is very easy. Already we have taken this kind of questions in electrostatics. Now in case 1, we have two masses, two equal masses m and m, separated by distance r. Now force between them is F. If first mass is doubled, that is 2m. Second mass is halved. Halved means m by 2. And distance between them is also halved. Now the new force is F dash. Once again question is, what is the ratio of F by F dash? What is the ratio F by F dash? Okay. Pause the screen and you can try. Okay, come back. See, first I will write in case 1, F is equal to capital G m into m by distance square. In case 2, f dash is equal to capital G remains same. First mass is 2m. Second mass is m by 2. Distance is r by 2 square, means you know it is r square by 4. This and this will be cancelled. Then f dash can be written as capital G Next question. Already this kind of questions we have taken in electrostatics. Once again, here consider 3 masses 2m m are separated by distance, say r, and another mass capital M which is also placed at a distance r from here. Question: what is the force on capital M? Force on capital M. See here. In this case, 2m will attract capital M, so experiences force this side. If I say it is F1, similarly small m also attract capital M, so this force, if I say F2, is this side. It means this capital M is experiencing two forces, F1 and F2. Therefore, the net force is given by F1 plus F2. Next, see here, as you know, in Newton's Newton's law of gravitational force, see here, capital G is, when we are adding these two, capital G remains same. So why should we write again and again? I can take it as a common. And we have to take product of two masses. Whenever I am taking a product of 2m and m, capital M, and m and capital M, in both cases I can take capital M same common, so I can take it as common. Now mass divided by distance is 2m. Distance is r plus r, 2r. 2r whole square is 4r square plus this is m, distance is r square. So here capital G, capital M, small m is common in both, and r square is also common. 2 ones are 2 2s are, so remaining is 1 by 2 plus remaining you can simplify. Right? One question. Next question. See, for the same problem, if I ask you, what is the force on small m? Force on small m. Okay, then see, this 2m will attract this small m this side. If I say F1, this capital M also attract this small m. hence it experiences for this side. I can call it as F2. Now this small m is experiencing two forces F1 and F2. Here both are opposite in direction. Therefore, net force is given by F1 minus F2. Once again, I will try to write directly. Instead of writing in steps, you can try with steps. I will try to write directly. See, once again, in both cases, capital G remains same. And when I am taking this product to m and m, and when I am taking this product m and m, in both cases, this small m is common. Therefore, I can take it as common. And here distance is r, here also r. Therefore, that is a distance is also taken as common, r square. Remaining is 2m minus m. Right? So this is the answer. Similarly, we can take other examples. Now I will give some examples. Try yourself. Okay. Just now we have taken two masses placed on single line. Now take three masses m, m, m are placed at three sides of equilateral triangle of side say A. Then what is the force on any one mass? Force on any one mass. Practice. See, I'll try to write directly. I'll try to calculate force on this mass. This m is attracted by this m. So this force is F1. And this m is attracted by this. So experiences force this side. If I call F2. You know, force is given by capital G, m1, m2 by distance square. If I take F1 or F2, capital G remains same. In case of F1, product is m and m. In case of F2, product is m and m. Means for both F1 and F2, product remains same. And in case of F1, distance is A. In case of F2, distance is A. Means for both, distance is also remains same. It means here F1 as well as F2 both are equal. And you know, all three sides are equal. Hence, you can say angle is 60 degree. As you know very well, when two equal forces makes an angle of 60 degree, resultant force is equal to root 3 times of one of them. One of them means I will write F1 or F2. That is capital G. Product is m into m is m square. Distance is a square. Right? Next. Another example. Same, you can take triangle. Okay. It's very easy. As you know, it is say it is a 3 meter, it's 4 meter, here it is 4 m, it is 3 m. Here say m naught. What is the force on m naught? Okay. See here, for this m naught will experience two forces now. One due to 3m, another due to 4m. This 3m will attract m naught. Hence its force will be this 35, say F1. This 4m also attract m naught. Then this force will be this side, say F2. You know F1 and F2 are perpendicular to each other. That is, angle between them is 90 degrees. Then what is F1? Force between two masses, same. Capital G, m1 into m2 means I can write 3m into m naught divided by distance square. Distance is 3 meter. 3 meter square means it's 9. So directly I can say capital G, capital M, m naught by 3, because 3 ones are 3 threes. And F2 is equal to capital G 4m into m naught divided by distance square means 4. 4 square is 16. 4 ones are 4 fours are. So directly I can say capital G, capital M, m naught by 4. Then, you know, when two are perpendicular to each other, resultant is given by under root of sum of their square. F1 square plus F2 square. Now directly you can write, if you simplify, you may get capital G, capital M, m naught in bracket 1 by 3 square plus 1 by 4 square. Remaining you can calculate yourself. This is the second example. Now the third, next question. See, set is capital M,